Hello, everyone. So we're doing chapter 11, 11.1, and I want to remind you that everything in chapter 11 is going to be very new for you. Take things slowly and steadily, and whatever you do not plan to cram for anything in chapter 11, okay? It is genuinely brand new mathematics that we're doing here. And it will take time for you to build up any intuition, understanding for how things should go. So we're talking about sequences right now, which form the foundation of infinite series, which we will talk about for most of chapter 11. And we're talking about limits. So I want to point out that most of the usual limit laws for normal functions over over an interval hold also for our sequences. Okay, and in fact, we even have a theorem here that says that if you have a limit that holds for a function of x, so that would be defined on an interval going out to infinity, for instance, then the values of that function going with a sequence make it so that the sequence will also have the same limit. Okay, so we can exploit that to just this one theorem right here to solve many different limit problems. And that's what we're going to do right now in these next two examples is show you how that should look. Okay, what's the logic going on behind things, and how does that make things need to be written? So this sequence right here, if we plotted it, for instance, take a look at this gigantic term in the denominator, there would be kind of no reason to plot this because all of the numbers would have ridiculously large denominators, and you're not going to be able to resolve anything on a plot. Okay, they're all very tiny numbers. But since we can think about the related limit of a function defined on the entire real number line in the same way. So notice how I am changing all of my n's for x's. This is very important. N's denote integers, whilst x's denote values from a continuum, okay, from the real number line. Now, since this thing right here happens to be infinity over infinity form, right? I can use L'Hopital's rule on this thing. And the only reason I'm able to do this is because I can take the derivative of a function which is defined to be a continuous curve. You cannot take the derivative of this thing over here, okay? I never want to see you taking derivatives of n's. We can't take the derivative of this because it is not a smooth function, okay? It's a bunch of disjointed points only plotted for integer values of n, okay? But this is very different. It's a smooth function, and I can take the derivative. Let's see, the derivative of the numerator here would be 8x plus 2, and the derivative of the denominator would be 14x plus 10 to the 100. And it turns out that this is, again, another infinity over infinity form, right? So I can do another application of L'Hopital's rule. Taking the derivative of the numerator, we get 8, and the denominator, we get 14. And so the result of this limit here is, what, 4/7. Okay. Now, since that happens, and because this function is the same as this function on the integer values of inputs, we can say, according to this theorem, right? Because what I did right here is I found the limit of x, of f of x, is this guy, and then this happens to be equal to this. So maybe I'll put in some explanatory text here. This is my f of x. This is my a sub n. Okay, and since that happens, and f of n is equal to a sub n, and the limit of my f of x was equal to 4/7, then the limit of my a sub n is also equal to 4/7. Okay, so this is the appropriate way to write this. You must switch to x's. All right, that's part of the proper notation that we will be grading on. Okay, so one note about doing this. You must switch to x's. To do things that can only be done for functions on a continuous curve. Okay? To do things which can only be done, or maybe which can't be done, for discrete valued functions. Functions on the domain. Of integers. Okay, n's mean integers, x's mean real numbers. Okay, but because we have these rules here, we don't always need to do so. Okay, like we said, most of the laws of 1.6, most of the old limit laws that you're familiar with, also apply to sequences. So let's go ahead and do this guy right here. For instance, I want to take the limit as n goes to infinity of this expression, then I can do something that doesn't require me to switch to x's. This is the technique we learned before we learned about L'Hopital's rule to do these types of functions, these types of limits, excuse me. Multiply by a number to put numerator and denominator on a common footing. Okay, you can notice that the denominator now, if I move this through, because the denominator is the same as 1 over root n squared, will distribute through the two terms in this denominator, leaving me with a 2 and a 1 over n squared. So I have now put my denominator, oops, my numerator is now just an n. I've now put my denominator on sort of a finite scale. The denominator used to be blowing up to infinity, right? This denominator blew up to infinity. But because I put it on this scale, it is now approaching a nice number. And I can use basic limit laws now in order to evaluate this. So this will equal infinity, since the limit of the denominator portion would equal this by continuity. Right, I'm plugging in a value inside of the square root there. And the way I get the value is by knowing that the limit of a 1 over n squared is equal to 0. Okay, so notice I did not switch to x's here because everything that I did was algebraic. Nothing here requires me to take derivatives or do anything that requires a domain of an interval. Okay, so these two types right here are important, and you should review exercises or examples 5 and 6 in chapter 11 for more of this.